So in the last video, we did a lot of work with average rate of change. And essentially the big takeaways were, if I give you a function, whether I give you that function geometrically by providing its graph, or algebraically by providing the equation of that function, I want you to be able to figure out the average rate of change between two different x values. So in this example, the two different x values that were given were -2 and 3, and we figured out the corresponding y values by plugging them into this equation. In this example up here, the two x values we were given were also -2 and 3, and this time we figured out the corresponding y values by just looking at the graph and figuring out the y values. And the really important takeaway from last time is this idea of average rate of change is really just the slope of the secant line that connects 2 points on a graph. And because we're talking about the slope of a line, we can take advantage of some of the stuff that we learned in a previous section and kind of exploit our slope formula to come up with this average rate of change formula. So there's kind of a quick recap of what we did in previous videos. In this video, I'm going to start with what might appear to be kind of a disappointing statement. It's a confession. The confession is all that stuff that we worked on kind of hard in the last few videos isn't really that important, I guess. I mean, maybe that's overstating it. You definitely need to know how to do that. But that's not the end of the game. Really, our interest in average rate of change will not be between two numeric x values like -2 and 3. But instead, it'll be from one numeric x value, like the number 4, to a mathematical expression like 4 plus h. So we're still going to be figuring out the average rate of change, and our average rate of change formula will still be the exact same as it was in the previous videos. To figure out the slope, I got to take the change in y divided by the change in x, the rise over run if you want. So if I'm calling my function f of x, and my two x values x1 and x2, then to find the change in the x coordinates, I would just subtract those two x values. And to find the change in the y coordinates, I would just subtract what comes out of the machine when I put those x coordinates into the machine. In other words, f of x2 minus f of x1. And if you're just given this formula with no context, it's kind of intimidating looking. But once you kind of understand the ins and outs of this formula, maybe you can just see that there's kind of some slope ideas going on here as I take the difference in the y's and divide it by the difference in the x's. Anyways, all I want to do is apply this exact same formula, except instead of having numbers in place of x1 and x2, having 4 and 4 plus h instead in place of x1 and x2. And I'll show you how to do that shortly. It'll turn out it's related, but honestly, it's a little bit harder, and it's going to involve a little bit more complicated algebra. But before I get there, I don't want to take you down this kind of perilous algebraic path without explaining a little bit about why we're doing what we're doing. So why? What in the world does the average rate of change from 4 to 4 plus h, for example, represent? Well, if you go back to the very first example in this section, when we modeled position as a function of time, I talked about how in calculus, a really important question is understanding instantaneous speed. My speed at a given instant. How fast am I walking 1 hour into my hike, for example? And it turns out that's really, really challenging to figure out. I mean, we made some general conclusions about how 1 hour into my hike, I'm hiking faster than I am 8 hours into my hike. But it was hard to really wrap our heads around what instantaneous speed represents. But there's good news. Average speed is something we can figure out. Average speed is just the slope of the secant line connecting 2 points. If I want to know the average speed from time 0 to time 1, all I got to do is figure out the slope of this line in orange that connects this point where x equals 0 and this point where x equals 1. That's the average speed over my first hour. That's not the instantaneous speed at this point. To figure out the instantaneous speed at this point, what I need to do is have an idea of how steep the graph is at this point. The slope of the curve, loosely speaking. Unfortunately, we don't have a formula for slope of a curve. We only have a formula for slope of a line. This little trick that I'm going to show you in this video with the 4 and 4 plus h will allow us to make that jump. It'll allow us eventually, probably not in this video, to bridge the gap between average rate of change and instantaneous rate of change. And I can even kind of talk about how that's going to happen. Here's the idea. Suppose you want to know the instantaneous speed or instantaneous rate of change of this function f of x at the point where x equals 4. So at this point right here, you want to measure how steep the curve is. Well, that's challenging because our formula for the steepness of a line involves two different x coordinates. But the minute I involve a second x coordinate, like one up here at 5, then I'm no longer talking about the instantaneous speed at this point, but instead the average speed over this interval. So how do I get around that? Well, what I'm going to do is I'm going to use this formula. This formula demands that I have two different x values. So I'll make one of the x values 4, and the other x value, I'll make it 4 plus h. What is 4 plus h? 4 plus h represents some imaginary point that is just a tiny bit more than 4. So maybe for the sake of the picture, I'll put it right here. But really what we're going to do is we're going to let this second point get infinitely close to this point once we learn some new concepts that we'll need for calculus. We won't learn those concepts in this section, so right now it's a little bit abstract, but the idea is we want to have two different points so we can use this formula. We can't use the x-coordinate 4 twice, because if we did, we'd be dividing by 0 here and our formula would blow up. So what do? We're like, well, we know we can't use the same point twice. Let's make one of the points 4, and we'll make the other point totally different. 4 plus h. That's different from 4, right? You're like, well, yeah, I guess. I mean, I don't know what h is, but 4 and 4 plus h look like two different things. Okay, cool. We'll plug those into this formula, and that will give us an expression. And later on, we'll learn how to manipulate that expression so that this second point can, loosely speaking, be moved arbitrarily close to this first point. If I completely lost you with all of that, great news. It doesn't matter. You don't need to understand these complicated concepts right now. Right now, we can do this completely abstractly, not understanding at all why we're figuring out the average rate of change from 4 to 4 plus h. We just need to know how. That's the only goal for this section. And the good news is how? It's not that bad. Just plug them into this formula. What am I talking about? Let's finally get to an example. I'm like way too far into this video to be getting to my first example. Suppose I give you this function, f of x is x squared minus 3x minus 2, which you might remember is the equation of this graph right here. What I want to do is calculate the average rate of change of this function on this interval. So I'm given two different x coordinates. The first one is 4, and the second one is 4 plus h. And I know that feels a little bit weird, but it'll turn out that it works just the same. To figure out the average rate of change, we have this formula. It says that we need to figure out the difference in the x coordinates and the difference in the y coordinates and divide those two differences. We're given x1 and x2, so we're halfway to the point where we have the 4 pieces of information that go into this formula. We just need to figure out f of x1 and f of x2. Let's do it. What's f of x1? Well, that's easy. You're telling me x1 is 4, so f of x1 is just f of 4. How do I figure out f of 4? Simple. I have this blueprint for this function right here, which tells me what comes out when x goes in. So I can use that to figure out what comes out when 4 goes in. Just copy exactly what you see written right here, but change all the x's into 4's. So it would be 4 squared minus 3 times 4 minus 2. It's 16 minus 12 minus 2. It's 2. You're like, yeah, that works out fine, but over here it's not going to work out so nicely. Well, yes and no. I mean, there's no reason we can't put an expression like 4 plus h into a function. I still need to know what f of x2 is equal to, because that's part of my formula down here. To figure out f of x2, what I want to do is take this thing x2, which is 4 plus h, and put that into my machine. So I have to evaluate f of 4 plus h. That might seem more complicated than evaluating f of 4, but it's really not. You do the same thing. You copy exactly what you see up here, except you change all of the x's, the generic input, into 4 plus h's, the input in question. So what would come out? Well, instead of x squared, I would have 4 plus h squared. And instead of subtracting 3 times x, I'd subtract 3 times 4 plus h. And then I'd still have this minus 2 right here. F of x2 is this expression. It's not a number like we see over here because my input is not numeric. Because my input is an expression, my output ends up being an expression. But that's totally fine. I now have the 4 pieces that I need. 1, 2, 3, and 4. And I can take those 4 pieces and plug them into this formula. What happens? Well, let's see what happens. F of x2 is this mess. It's 4 plus h squared minus 3 times 4 plus h minus 2. That's just f of x2. From that, I want to subtract f of x1. F of x1 is 2. So I have to subtract 2 here. Don't get confused with these two different 2's. This first 2 is part of f of x2. This second 2 is f of x1. That's your answer? No, that's just the top. That's f of x2 minus f of x1. I still need to divide that by x2 minus x1. What's x2? x2 is 4 plus h. So I have 4 plus h. And from that, I want to subtract f of x1. F of x1 is 4. So I got 4 plus h minus 4. Now what? Well, now kind of depends. If you're asked to simplify this thing, we can simplify this thing. But if you're not worrying about simplifying, we're done. This expression right here represents the average rate of change of this function from 4 to 4 plus h. This expression right here tells us the slope of the tangent line of this function from 4 to 4 plus h. It's the slope of this line in red right here that connects 2 points on this curve. One of those points has an x value of 4, the other one has an x value of 4 plus h. Note, I don't know what h is, it's a variable, so I don't know where to put it in my picture. So I put it here close to 4 just to kind of illustrate the point, but the idea is we can't really calculate the slope of this line because we don't know what h is. So if h is 5, then this second point will have an x-coordinate of 9. If h is 1, then this second point will have an x-coordinate of 4 plus 1, or 5. It would be up here. Depending on what h is, this second dot is going to move, and as this second dot moves, the slope of the line connecting the dot at 4 and the dot at 4 plus h is going to change. How is it going to change? Well, according to this formula right here. If I want to figure out the slope of the line from 4 to 5, for example, well, to make this second dot 5, I need h to be 1, because 4 plus 1 gives me 5. So all I'd have to do is take this expression and change all the h's into 1s. But I don't want to know the slope of the line from 4 to 5, because if I did want to know the slope of the line from 4 to 5, I would have made x1 and x2 4 and 5 respectively, not 4 and 4 plus h. That would have made this way simpler. I don't want the slope of the tangent line from 4 to 5. I want an expression that tells me the slope of the tangent line for any value of h. And this expression right here does exactly that. Before I end this video, I want to make a couple comments on this answer. This expression simplifies really nicely. I'm not going to simplify the top just yet, but note that in the bottom, I have 4 and minus 4. Those can cancel out, and I'm left with just an h. And that's not a coincidence. We will always be left with an h in the denominator anytime our two x values are just a number and that same number plus h. Because no matter what number I'm given here, say this was 11 and 11 plus h, then my denominator would be 11 plus h minus 11. And those 11s would cancel and I'd still be left with this h. The fact that there's an h in the denominator here, when I start to simplify this expression, is not a coincidence. That will always happen. The other comment that I want to make is this h cancels out really nicely. You can't see it right now, but if I simplify the numerator a little bit, I'll end up with an expression where I can cancel this h. And that's not a coincidence. Let me go through and do it. 4 plus h squared, you have to think FOIL for that. So 4 plus h times 4 plus h, you'd get 16 plus 4h plus another 4h, in other words 8h plus h squared. That's just this first set of parentheses. I then need to subtract 3 times this set of parentheses, so I can take the negative 3 and distribute it through, and I get negative 12 minus 3h. And then I still have this minus 2 and this minus 2, so I have minus 4. But look what happens here. I have positive 16 minus 12 minus 4. Those all cancel out. This, and this net to 0. So then what am I left with up in the numerator? Well, I got this h squared term, and then I got 8 of these h's minus 3 of these h's, so I have 5 of these h's. Down in the denominator, I just have an h. If you're a little bit more advanced algebraically, you might notice that because each of the terms in the numerator, remember the terms are the things separated by plus and minus signs? Because they all have an h in them, I can factor out an h from the numerator, and I'd be left with an h here, because the h squared has 2 of the h's and I'm pulling one of them out, plus a 5 here, because here I have 5 times h, but I'm pulling the h out. And then I'm dividing that by 8. And because I can cancel over multiplication, when I get to this stage, these h's cancel, and I'm left with just h plus 5 as my answer. That might not seem like a big deal that this simplified nicely, whatever that means, and I was able to cancel out that h, which is always going to appear in the denominator. But it turns out that's super important. The ability to cancel out the h in the denominator will be the crux of calculus. Calculus wouldn't work if this didn't happen. And you're like, damn, so you better choose these functions really, really carefully so that the top simplifies really, really nicely so you can cancel out that h. No, I don't have to. For calculus reasons that we'll learn later, that h will always cancel out. That was not a coincidence. Sometimes it'll be relatively easy to cancel out that h, sometimes it'll be much more challenging algebraically speaking, and in the next video I'll take you through a bunch of examples showing you all the different types. But I don't want to worry about any of that right now. I want to focus on what's most important for you to get, and what you need to get out of this video is, it's going to be really, really important for you to calculate average rates of change, not between two different numeric x values, like, I don't know, 4 and 7, but instead between x values that involve expressions. And those expressions will always take on a certain type, and for now we can kind of think about them as a number, like the number 4, and then that exact same number plus the letter h. So it won't always be 4, but if this is a 9 right here, this is 9 plus h. And that's not just to make algebra work out nicely, that's to answer a very real world problem that calculus will be based upon, but we don't need to worry about that right now. I'm telling you this is what the problems will always look like. And you're like, all right, I can go through here blindly and I can figure out f of x1 and f of x2 if you give me x1 and x2, even if it feels a little bit weird because x2 is an expression, not a number. And I can gather those 4 pieces of information and throw them into my average rate of change formula. And I can completely ignore why I'm doing that and what that represents. I can just go through and show off all my algebraic skills that I've learned over the years, and I can simplify that expression. And a nice thing will always happen. The denominator will always simplify to just the letter h, and the numerator will always simplify to the point where you can cancel an h from the numerator with that h that is down in the denominator. And I can't emphasize enough how important this is. You'll be shocked at how much of this class is based upon this example that we just went through. So if it feels like I'm beating it to death in this video, I am, and I'm doing so on purpose.